Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jin Kim, and today we're going to learn how to know where we are. Not like where we are in life or where you're going in life, but literally, where on Earth are you and how can you show that on a map? That's right, it's time to learn about what latitude and longitude are, how they're different, and why they're incredibly useful for humanity. Let's get started. If I asked you right now, where are you? What would your answer be? You might say that you're home, at the Newmarket 277 Mall, in Birmingham, or driving in your car. There are many ways in which we can tell someone our location. We can use the name of the place that we're in. We can give a relative location, like in the cafe 2 shops to the right of the cinema, or even an address. But none of these options are particularly helpful when you're giving a specific location with no obvious landmarks. For example, if you're exploring the uncharted wilderness and you get lost, what location do you tell the rescuers on the other side of the radio? You could say, look for the mountain that looks like an eagle's head and go about 1 kilometer west near a large oak tree. But that might not be specific enough. To solve this problem, we use a coordinate system called latitude and longitude, which lets us use hard numbers to denote exactly where a location is, and we can look it up on a map. So today we'll learn about what latitude and longitude are, how the coordinate system works, and the history of navigation so you can understand just how important this system has been for humanity throughout history. But, of course, let's start off by explaining what latitude and longitude are to you as if you were a child. Have you ever played the game Battleship? You know, that board game you might have played when you went camping where you have to guess where your opponent's ships are hiding and shoot them down? When you want to shoot at your opponent's ship, you have to tell them where you're shooting at, so they can tell you if they've hit the ship or missed. If you just said, I shoot over there, that's not very helpful. Your opponent will have no idea where you mean. If you said 2 squares from the middle of the board, that's also not great, because you need to tell them 2 squares in what direction, and where middle is. Turns out, telling someone an exact place without, showing them is kind of hard. Which is exactly why Battleship has letters and numbers along the map on the side, so you can tell your opponent exactly where you're aiming. The map is a 10 by 10 square, and along the bottom of the square, you'll see that each square is marked A, B, C, and so on. Along the left side of the square, it'll be marked 1, 2, 3, and so on as you go up the line. This means that you can use coordinates. So, if I was to say, I'm shooting at B4, that means you need to look at your map, go to the bottom, and move your finger from left to right until you hit the square marked B. Next, you move your finger straight up while looking at the left of your map until your finger lines up with the number 4. The square where your finger is? B4. Huzzah! Oh, but you missed. Tough luck, kiddo. Better luck next time. Anyway, this system is super simple, but super effective, because all you need to know is how the left to right horizontal line at the bottom and the up to down vertical line at the side are labeled and marked, and how to count. So we use exactly the system on maps as well, so we can know exactly where on Earth we are, or where other places are. But we can't just use A, B, C, and 1, 2, 3 on Earth, because Earth is a round, 3-dimensional ball, not a flat 2-dimensional square like Battleship. Which means we need a slightly different system. On Battleship, the horizontal line telling you if the point is on the left or right side of the square were marked A, B, C, and so on. On Earth, we use something called longitude, which are the coordinates for west and east. And instead of A, B, C, longitude is marked by degrees, because you're essentially dividing a circle. So you start at 0 degrees, and then you say which direction you're going towards. So if you're moving a quarter way around the world eastward from 0 degrees, your longitude would be 90 degrees east, because a circle is 360 degrees, and 360 divided by 4 is 90. Latitude is the other half of the coordinate system on Earth, and this replaces the 1, 2, 3 on the vertical lines on Battleship. This tells you how north or south you are from the equator, the invisible belt around the Earth's waist. And we use degrees for this as well. So if you start from the equator and go halfway to the North Pole, you'd be moving 1/8 of the circle, so you'd be 45 degrees north. Combining the two coordinates, latitude and longitude, you would say this point is 45 degrees north, 90 degrees east. And then anyone can look at a globe or a world map and point out exactly where you are. That's the magic of coordinates. And it turns out it's super important to know where you are on Earth when you're an explorer sailing uncharted oceans. Or you need to drill 2 tunnels from either side of a mountain and meet in the middle. Or, if you need to crush your friend in Battleship and sink all their ships. Welcome back. Latitude and longitude are very deceptively complex. You've probably heard of the two terms before, and you might even know that latitude are the flat horizontal lines on a map dividing the world from north to south, while longitude are the long vertical lines on a map dividing the world from west to east. But the more you think about them, the more your brain will wrinkle. Like, what on earth does 37 small circles, 65 quotation mark, 72 speech mark, n even mean? And what is the importance of knowing all of these? I'm content using Google Maps and not going on any explorations to discover new lands and waters. And yet, you live on this Earth, so you should probably know a little about how people navigate across the globe, both past and present. Plus, it's quite interesting. Alright, so to recap, latitude and longitude are special coordinate systems that let us map exactly where on the surface of Earth we are. If Earth was a flat rectangle, we'd be able to use the simple Cartesian coordinates with an x-axis and a y-axis, just like Battleship, chess, and, if you're old school enough to remember them, paper road maps with grids drawn on them so you can find places. But alas, despite the conspiracy theorists, the Earth is a 3-dimensional, round spheroid with curves. So square grids don't work nicely. For one, the map loops around, so you go A, B, C, and so on until you get to Y, Z, back to A. So letters don't work as well. And for another, you can't nicely divide it into even units of distance because of the sphere shape. To illustrate this, if you were to divide the horizontal line along the thickest part of Earth, the equator, into 10,000 units, each unit would be about 4 kilometers long, because the equator is 40,075 kilometers in length. But if you were to take this unit and apply it to the horizontal line that loops around the Earth over where Taiwan is, the circumference is only 36,788 kilometers. And if you go all the way down to the South Pole, you can circle the Earth from west to east completely within a few seconds just by swinging on a pole round and round going whee! So, instead of units, we use angles. Because the Earth is roughly a sphere, if you cut it in half and looked at the cross-section, it would be a circle. Since we know that a circle is made up of 360 degrees, we can divvy up the circle like a pizza or a pie, and use the degrees to note down how much of the circle's edge we've traveled. This means that if you walked from one point on Earth to the opposite point, or the antipode if you want to sound smart, in a straight line, you would have traveled 180 degrees off the Earth. Get it? Quick side note here. You should know that the Earth isn't exactly a sphere, because as it spins, the centrifugal force makes the Earth slightly thicker along the equator, compared to the circle that connects the North Pole to the South Pole. This is why we call it a spheroid instead of a sphere, because it's sphere-ish. So if anyone ever rudely points out that you're looking thicker around the belly, just tell them it's because of centrifugal force. Anyway, back to angles. Now that we can divide up the surface of the Earth into segments, we need a reference point so we can tell where 0 is. For latitude, it's super easy. We just mentioned that there's a very handy central reference point, the equator. Because latitude marks the north-south coordinate, the equator is a perfect reference point because it's bang on in the middle. So we call the equator 0 degrees of latitude. From here, you can move up 90 degrees north to the North Pole, or 90 degrees south to the South Pole. Alternatively, you can also use plus 90 degrees for the North and minus 90 degrees for the South Pole. Between these points, you have horizontal rings parallel to the equator, giving the Earth horizontal stripes. These lines are funnily just called parallels. If you've ever been to Korea or heard about the 38th parallel, this is what it's referring to, a line marking 38 degrees north latitude. There are 5 parallels that are quite important to know about. The first is equator, because it's 0 degrees. The next two are the Tropic of Cancer and the Tropic of Capricorn, which are respectively in the North Hemisphere and South Hemisphere and essentially mirror each other. You will hear about these lines in various contexts, such as that coffee plants usually are only cultivated between these two lines of latitude. The reason the tropics are important is that they are the latitude at which on a solstice, June 21st for the Tropic of Cancer and December 21st for the Tropic of Capricorn, the sun is directly overhead at noon. That means that if you were to be standing on any place along the Tropic of Cancer on the June solstice, you would see that a flagpole or any stick perpendicular to the ground would have no shadow. We covered this concept briefly in our zodiac episode, where we learned that the Earth is spinning on a tilt in relation to the sun, which is why we have seasons. And that's why it's the Tropic of Cancer and Capricorn where the sun is directly overhead on noon on a solstice, rather than the equator. Anyway, the Tropic of Cancer will come up later in the episode, but for now, that's all you have to know. You don't even have to know the exact latitudes for the two tropics because they shift over time because the Earth's tilt wobbles slightly. But if you're interested, at the time of recording, the Tropic of Cancer was 23.43614 degrees north, and the Tropic of Capricorn, the exact same numbers, but south. The last two parallels you have to know about are the Arctic Circle and Antarctic Circle, which mark the very cold polar regions. Alright, so that's the gist of latitude. Parallel horizontal rings going north and south of the equator, marking out how north or south you are on the world. What about longitude? These are vertical lines going from the North Pole to the South Pole, and they mark our west-east position. But we've got one small problem. With latitude, we know exactly where the center is because of the equator. But with longitude, there is no obvious center point, because technically, every point can be east of another point. You just have to go around the world enough. So, humans being humans, we arbitrarily set the 0 degrees at Greenwich, United Kingdom, and decided to call it the prime meridian, because everything is a social construct. Anyway, this line plus the international date line, which roughly corresponds to the 180-degree meridian, that's what we call lines of longitude, divide the world into the western and eastern hemispheres. And just like latitude, we use angles as units. So if you start in Greenwich, UK and travel eastward by a quarter of the Earth's circumference, then your longitude would be 90 degrees east. This is particularly relevant for longitude because of the issue we mentioned before of spheres having unequal circumferences at various points, if you slice in parallel lines. Like when you're slicing onions, the slices get smaller and smaller in size as you cut towards the root. So now that we have defined latitude and longitude, we can mark any coordinate on Earth. The convention is that you say the latitude first, then longitude. So if I wanted to tell you the coordinates for the Eiffel Tower, I would say that it's 48 degrees north, 2 degrees east. And then you take a globe that you have handy, like every good person should, look for the equator, and go up towards the North Pole 48 degrees out of 90. Then move your finger horizontally until you find the prime meridian intersecting Greenwich. Then you go 2 degrees to the right to the east, and voila, you'll have your finger over where the Eiffel Tower is. But hang on, the Earth is pretty dang huge. We just said that the equator is 40,075 kilometers wide in circumference. The circumference going north to south is ever so slightly smaller at 40,007 kilometers. Which means that each degree of latitude is about 111 kilometers. A degree of longitude is variable depending on what latitude you're at because of what I'll now call the onion ring problem. But even so, 1 degree is a huge margin of error on a map. Imagine telling you a coordinate that actually marks out 100 by 100 kilometers square. That would be like looking for a needle in a haystack. So to make things more accurate, we divide each degree of latitude and longitude by another factor of 60, which we call minutes. And then each minute can be divided into, can you guess it? 60 seconds. Yep, we're bringing back the sexagesimal system, baby! Which is not so sexy to do calculations with, but it works pretty well when you're working with circles and spheres. We mark degrees with the small circle that you're used to from geometry and temperatures. The minutes we mark with a single apostrophe, and seconds with double apostrophes. Our latitude-longitude coordinate system will narrow you down to a maximum 30 by 30 meters square, which is not that bad really. The seconds can even be marked down to 1 decimal place, which further improves the accuracy to a 3 by 3 meter square. So, the actual coordinates for the Eiffel Tower would be written as 48 degrees, 51 minutes, 29.6 seconds north, 2 degrees, 17 minutes, 40.2 seconds east. And that's how latitude and longitude works. Now, you're probably thinking, sure there's a bit of maths involved, but latitude and longitude seem pretty easy to grasp. How's Jin gonna make an entire podcast episode on this topic? Well, I got you covered, because turns out, as simple as the theory of latitude and longitude are, the practicality of figuring out what latitude and longitude you're in is not an easy task. So much so that figuring out how to calculate latitude and longitude is considered one of the finest scientific achievements of humanity. Let's take a short break and we'll take a history lesson on how humanity figured out how to map the world. Navigation skills have been super important to humanity since the dawn of time. In the early days, when we were hunter-gatherers and agriculture hadn't been fully developed, it was not unusual for a tribe of people to run out of food or other resources in an area, or were displaced by disasters and wars and other dangers, forcing them to find a new home. And if you've ever been lost in an unfamiliar place, like when you're traveling, you know just how useful it is to have a good map, or a friend who can get you unlost. So ancient people all around the world were interested in how to map out areas as they explored and traveled, and love to tell stories of adventures in faraway lands. Over time, clever people figured out that if we could come up with a coordinate system, like we described with the battleship example, then it would be much easier to draw accurate maps and tell people where things were exactly, so that they wouldn't travel the wrong direction and starve to death in the desert or something like that. Which means that even as far back as ancient Greece, people were interested in a system like latitude and longitude. Because people had figured out the simple navigational tools like distance and the cardinal directions, north, east, west, and south, they just needed a way to tell people exactly how far north, etc. you needed to travel from one city to another. And contrary to popular belief, even the ancient Greeks knew that the Earth was round and spherical, not flat. The myth that medieval people thought that the Earth was flat is completely false, and it was widely accepted for the past 2,000 years plus that the Earth is a giant ball. To illustrate, we introduce one of the key figures of our episode, the badass Greek mathematician Eratosthenes. Eratosthenes was a polymath, basically an actual know-it-all who dabbles in everything. He was such a clever cookie that he went to be a chief librarian of the Library of Alexandria. One day, Eratosthenes heard about a peculiar phenomenon in a city called Syene, about 800 kilometers south of Alexandria where he was working. It was said that on the summer solstice, people noticed that a stick planted in the ground pointing straight up would have absolutely no shadow at noon, when the sun was at its highest point. Even more bizarre was that if at this time you looked down a well, you could see right down to the bottom of the well, because it would be fully lit by sunlight. Which, if you've ever tried doing, is never the case. There's always some shadow at the bottom of a well. Now, most people would have just said, cool story, bro, and moved on with their day. But Eratosthenes pondered this. He did some simple experiments where, on the summer solstice, he would plant a stick in the ground and track how long the shadow was throughout the day. He noticed that as it approached noon, the shadow got shorter and shorter and shorter because the sun was rising higher in the sky over him. But when noon arrived, the stick would still have a short shadow. Then the shadow would slowly get longer as the sun started moving westward in the afternoon. So how come in Syene, merely 800 kilometers away, you could do the cool no-shadow sticks trick, but you couldn't repeat it in Alexandria? Was it all just fake news? Nah, Eratosthenes thought, there's something here. If the Earth was truly flat, then he should have been able to replicate the no-shadow trick in Alexandria as well. But because there's a discrepancy in the length of the shadow at the exact same time, the surface of the Earth must be curved, and the sunlight is hitting the Alexandria stick at a slight angle, while it's pointing directly down the Syene stick. Which means that the Earth must be round. Boom! Eratosthenes now had proof that the Earth was round, even without any satellites or pretty pictures of Earth from the moon. But he went deeper than that. He used some simple geometry and realized that with this information, he could calculate just how big the Earth was. What he did was this. First, he measured exactly what angle the sunlight was hitting the pole at Alexandria at noon on a summer solstice. because all you have to do is draw an imaginary line from the tip of the shadow to the tip of the stick, and you make a right-angled triangle. He figured out that this tiny angle was 7 degrees. Because he knew that the sun must be super far away from Earth, making sun rays essentially parallel as they hit Earth, he figured out that this 7-degree angle is the same angle that you would get if you extended the two sticks in Alexandria and Cyan all the way to the center of the Earth and made them meet. Like a really, really thin pie slice, because you're on a diet. 360 divided by 7 is roughly 50. So that means that the distance from Alexandria to Cyan is about 1/50th of the circumference of the Earth. So Eratosthenes hired a man to walk the distance between the two cities to calculate exactly how many paces the distance is. And don't worry, he didn't just pull some random Joe Blog to go walking 500 miles. This was professional work carried out by Bemetis, who prided an accurate measurement of long distances using paces. Anyway, he learned that the exact distance between the two cities came to 5,000 stadia, or about 800 kilometers. Therefore, the circumference of the Earth must be 800 times 50, which is 40,000 kilometers. Which is pretty dang close to the actual circumference of the Earth. That's a less than 0.2% error, considering all Eratosthenes used were some sticks, footsteps, and some clever brain work. Eratosthenes is considered the father of geodesy, the science of measuring the Earth and everything on it. Anyway, this shows you that even 2,300 years ago, clever people had figured out a lot about what the Earth looks like and how we might map out the surface of the Earth. So now we come back to latitude and longitude. We've established that it's a useful and important system, especially on a spherical Earth. But how will we actually calculate and implement it? Turns out, latitude is pretty easy to figure out. All you need is figure out how high the sun is in the sky on the solstice, and boom, you've got a reference point. Remember the no-shadow trick in Cyan? Well, if you were paying attention, that trick should sound familiar because I literally just told you about it a bit earlier in the episode. It's because Cyan pretty much lies directly on the Tropic of Cancer, the latitude parallel where the sun is directly overhead you at noon on the summer solstice. By the way, just so you're not confused, we're talking about solar noon, as in when the sun is at its highest point in the day, not exactly 12 p.m. Anyway, you can imagine that if you were in Cyan, the angle that the sun is at on the noon of summer solstice is 90 degrees. It's pointing directly down at the stick, therefore no shadow. This is because 0 degrees is the horizon and 90 degrees is directly above you. Using this as a reference point, you can tell how far north or south you are from the Tropic of Cancer, because the further you move away, the lower the angle the sun would be at on the summer solstice. This is pretty useful, and it's how the ancient Greek explorer Pytheas measured out different latitudes of various cities and lands he traveled to in 325 BC. But it's not as clean of a system as what we've described, where the equator is 0 degrees and the north and south poles are 90 degrees. This is where Polaris, the North Star, shines. Because fortunately for us, Polaris happens to be positioned directly over the North Pole of Earth. And unlike the Sun, stars are so far away that they're pretty stationary in the night sky, other than moving east to west as the night passes. The only thing that changes is the times that they rise and fall depending on the seasons. Unless, of course, you're traveling north or south. If you were to look up in the night sky standing exactly on the North Pole, which would be hard because there's no land there, only sea, you would see Polaris directly overhead. So you could say that the North Pole is 90 degrees north latitude, because Polaris is 90 degrees from the horizon at night. Easy peasy. Now, let's travel all the way down to the Eiffel Tower again. Remember how we said that the latitude of the Eiffel Tower is roughly 48 degrees? This means that if you were on top of the Eiffel Tower and looked up at the night sky to search for Polaris, you would find that it is 48 degrees, or just over halfway between the horizon and directly overhead you, above the horizon. To imagine another way, draw a line from you to the horizon. Then, draw a line from you to Polaris. The angle that these two lines make as they meet at your feet will be 48 degrees, if you're at the Eiffel Tower. And that's how you calculate latitude. All you need is a wayfinding star and a clear night sky. The one big downside to this method is that Polaris is only visible in the northern hemisphere. If you were to look for Polaris at the equator, you'd just see it hovering on the horizon, which is why the equator is 0 degrees latitude. If you go any more south, Polaris would be under the horizon, so you can't see it. Instead, we can use the Southern Cross as a nearby guide to the celestial South Pole and figure out latitude that way. On a related note, please do bear in mind that the history of navigation that we're presenting here is a very Eurocentric, West-based history lesson. We're totally skipping over the incredible navigation skills of other cultures, such as the Polynesian people, who crossed the frickin' Pacific Ocean with great accuracy 2,000 years ago. Polynesian sailors also used stars extensively in their navigation, but also used lots of other handy things like bird migrations, ocean swells, and all sorts of memorized patterns passed down in stories and oral lessons, to effectively discover and inhabit most of the islands scattered across the wide, wide Pacific Ocean. There were streets ahead when it came to navigating the uncharted ocean compared to Europeans. Anyway, back to Europe, where they were all still figuring things out. As civilizations matured, navigation became more and more important because you wanted to know where resources and potential enemies might be, but also to establish trade routes with faraway lands, because gotta get them Roman glass and spices and high quality silk. But the need for accurate navigation really came up in the age of exploration in the 17th century. This is when we see the colonial powers such as United Kingdom, France, Spain, and the Netherlands realizing how much richer they could get if they were to discover new lands across the ocean full of resources, totally ignoring the people and cultures that lived there for thousands of years already, and choosing to violently oppress and murder them to steal their lands and goods with the clever use of flags. Oh, colonialism, the great evil elephant who we cannot and should not ignore in European history. Anyway, turns out navigating the high seas is much harder than navigating on land, because A, there's much less landmarks out at sea. That's why they call them landmarks, not sea marks. And B, the waves and currents and wind are constantly moving you about. Oh, and C, the constant threat of shipwreck and never finding land and dying of thirst or starvation or scurvy or mutiny. So, it became very important that people could figure out their location exactly using latitude and longitude. This is when we see many great strides in navigational instruments being developed, such as the Mariner's astrolabe, followed by the sextant, both of which could let you calculate latitude in the southern hemisphere. Alright, so we have latitude down, so all we need to do is figure out longitude and navigation will be super easy, right? Right? Well, here's the problem. Specifically, the longitude problem. Very annoyingly, turns out longitude is much harder to calculate than latitude. And this makes sense if you think about it. Latitude is relative to the equator, which is a fixed point. This means that even as the Earth rotates, the two methods we discussed earlier, measuring the height and angle of the sun at noon and measuring the height and angle of Polaris at night, works. Think about it this way. If you take a globe, spin it, and hover your finger over a point without touching the globe, the finger will trace a perfect line of latitude as the Earth spins. You can imagine this finger is light from Polaris. Because Polaris is so far from Earth, and it happens to be in the direction directly over the North Pole, it appears pretty much stationary in the night sky in the Northern Hemisphere, regardless of what time of night it is. This means the height or the north-southness of Polaris in the sky won't change regardless of time, and therefore you can use it for latitude through the night. But when it comes to longitude, we're trying to figure out east-westness. We mentioned how east and west directions work, like with Earth's rotation and stuff. There's no easternmost or westernmost point. Every place could be east or west of another location, if you just go around the world enough. This means you no longer can use the sun or stars like Polaris to figure out your longitude. Because as time passes and the sun and the Earth rotates, the position of the sun and stars all change, moving from east to west along the ecliptic. Ugh, how annoying. That said, it's not impossible, obviously. Clever people, such as Ptolemy of Greece living in the 2nd century AD, figured out that there was a sneaky variable you could use to calculate your longitude. Time. That's right, because as the Earth spins, it shows a different longitude line towards the sun every hour, every minute, and every second. Going back to our globe example, As your finger hovers over the spinning globe, you'll notice that the lines of longitude are increasing westward, going 0 degrees, 30 degrees west, 60 degrees west, 90 degrees west, and so on. Since it takes 24 hours for the Earth to rotate fully once, you can take the total longitude, 360 degrees, and divide it by 24, which gives you 15. This means every hour of time equals 15 degrees of longitude. This is a kind of confusing concept of how space and time are linked in this way, so we'll explain it to you in a simpler way to help you understand. Imagine this. You're a traveler starting your journey from London, which happens to be in the same longitude as Greenwich, as in the prime meridian, or 0 degrees of longitude. Before your trip, you set your watch to the local time in London. Now, let's say you were on a reckless sea voyage and suddenly had the urge to figure out how west or east you are of London. As in, what is your longitude? Well, because you have a watch set to London time, you can use the 1 hour equals 15 degrees of longitude rule to figure out what your longitude is. If you were to wait until solar noon when the sun is at its highest point, you'd know that it's roughly 12 p.m. where you currently are. If you were to check your London time watch at this exact time, you can figure out what the time difference is between you and London. So if it's 12 p.m. where you are and your watch says that it's 4 p.m. in London, you know that London is 4 hours ahead of you. This is pretty much how time zones work. Now, if you times 4 by 15, you get 60. Therefore, you are 60 degrees west of London, because that's how long it took for the Earth to rotate 60 degrees and get the sun to the right position. Just so you know, technically speaking, solar noon is actually not 12 p.m. on the dot usually. And time zones don't exactly obey the lines of longitude because convenience. So there's some calibrations you have to make, but the general concept still stands. Anyway, this shows you how you can use time to measure distance. How cool is that? And this sounds super easy to us living in 2024 when everyone carries a really accurate digital clock in our pockets or on our wrists. But if you think about it, accurate clocks haven't really been a thing for humanity until the past 300 odd years. People had sundials and water clocks to figure out roughly what part of the day it was, maybe up to the hour, but the ability to measure minutes and seconds with reliable accuracy is a much more recent technological innovation. Which poses a problem, because if you are going to use time to measure our longitude, you need to be bloody accurate. Say that your watch is a bit wonky and it's running 1 minute late. Sounds like a big whoop, right? But turns out it is a big whoop. Specifically, it's 0.25 degrees of longitude of a whoop, which at the equator equals about 28 kilometers. Imagine that you thought you were going home after a long, hard day of work, and you realize you've been dropped off 28 kilometers east of home. How pissed off would you be? Probably a lot less pissed off than if you were a sailor and that 28 kilometers was the error in distance to the nearest island, where you desperately need to find fresh water and food and vitamin C, because your crew are dying after an arduous journey on open waters. So, yeah, accuracy matters a lot when it comes to longitude. And unfortunately, even though accurate clocks such as pendulum-based grandfather clocks were becoming more and more popular and commonplace over the 17th century, a lot of this technology was not useful at sea. Because pendulum clocks need to be left undisturbed, the motion of the ocean would wildly swing the accuracy of the time on the clock, making it pretty useless as a timekeeping device at sea. Furthermore, the delicate metal components could warp and rust with the harsh conditions out at sea, meaning that sailors had no good ways to accurately keep time and figure out the time difference between where they were currently and back home. This meant that for most of human history, we just could not calculate longitude, which meant that there was no good way to know your coordinates, because you need both the X and the Y, or both the letter and the number on a battleship grid. But sailors gotta sail, so people tried their best. The main method of navigation was actually called dead reckoning, where you mark a spot on the map, figure out which direction you're heading and the speed at which your ship is moving, and essentially extrapolate out where your ship might be after a certain time period. This is what you can see from period dramas where the navigator or the captain is using a compass and navigational divider, mapping out where they might be if they were heading northwest and traveled 3 nautical miles. Oh, fun side note. Nautical miles are calculated using longitude and latitude. Since there's no landmarks out at sea to easily tell you if you've traveled a kilometer or a mile, sailors would use something called nautical miles instead to map distances. A nautical mile is defined as 1 minute of longitude along the equator, because this is where the distance between each meridian is widest, as per the onion ring problem. And 1 knot is the speed of traveling 1 nautical mile in 1 hour. So, there you go. The more you learn. Okay, back to navigating without longitude. As you can imagine, dead reckoning was not the best tool, because there's so many variables such as currents and winds that might set the ship slightly off course or affect the speed, meaning that dead reckoning was basically making an educated guess. And the name is apt, because a lot of sailors perished due to navigational errors. It's said that between 1550 and 1650, 1 in 5 ships was lost between Portugal and India. 1 in 5. Since sailors knew how to calculate latitude, they tried to use this to improve their navigational accuracy. If you had a starting location marked in a map, you could keep an eye on your latitude every day, travel along the same parallel of latitude either west or east, and you would have a pretty good idea of the path that your ship would take. This was called running down the westing or easting, depending on which direction you were traveling. And it was pretty good, but it was quite inefficient because you were forced to travel along parallels going west to east, instead of traveling in diagonals or the shortest path. And this, my friends, is the longitude problem. Navigating the high seas would be so much easier if you could just reliably calculate both your latitude and longitude. And you already know that you can use time to calculate longitude, but the technology didn't exist to produce a reliable clock that could work at sea. The longitude problem really became a headache in the 17th century when Europe was embarking on the age of exploration. We already talked about how the trade boom and rapidly growing colonialism meant that the European powers were racing to discover more new lands and better sea routes to optimize logistics. But all of this required navigational skills, and specifically a solution to the longitude problem. Even with all the resources in over 100 years, countries such as the UK, France, Spain, and the Netherlands all couldn't solve the longitude problem. They got closer and closer, such as old Galileo, the father of the scientific method, figuring out that you could use the orbits of Jupiter's satellites as a kind of universal clock to help calculate longitude. But again, this wasn't feasible at sea because his newly invented telescopes just weren't good enough for that purpose. And it became an even more pressing issue in 1707 when there was a high-profile maritime disaster case involving navigation error. After a skirmish with the French, British Admiral Sir Cloudesley Shovel, which definitely sounds like a randomly generated name, was leading his fleet back home. But the ships ran into a heavy fog and couldn't use the trusty sky to navigate them safely. So they leaned on the old reliable, really unreliable, dead reckoning method to try and map out the way. But due to shifting currents and winds and no way to update their dead reckoning positions due to 12 days of fog, the ships ended up crashing into the rocky Scilly Isles, sinking 4 out of 5 ships and resulting in the death of 2,000 people. This made the British Parliament say, enough is enough, we need to take this problem even more seriously. And so the Greenwich Observatory put out a challenge to the general public. Figure out a reliable way to solve the latitude problem and we'll give you £20,000, which sounds like a decent amount of money until you realize that after adjusting for inflation, that number is more like £3 million in today's money. So yeah, people were appropriately motivated and set out to solve the longitude problem once and for all. There were 2 main concepts that people focused on. Let's call them Team Moon and Team Clock. The first promising method was that using lunar distance. We won't go into the fine details, but it essentially relied on using detailed tables of expected distances between the moon and the sun and the other stars at a given time, plus rigorous calculations to derive the longitude. This method worked, but it was really hard to use. Like, the calculations would take upwards of 4 hours just to figure out the longitude. Plus, it relied on your database, or almanac, being accurate. Imagine doing a 4-hour maths problem while trying not to be seasick on a moving ship. And that's it, some navigators such as Captain James Cook successfully used this method to calculate longitude on his first journey to the Pacific. The second method went back to the concept that time equals distance and longitude. Why figure out a whole new calculation method when all you have to do is invent an accurate clock that worked on a ship? But, like I said, this was a very difficult technical task, because pretty much every method of clockmaking failed spectacularly on a moving ship. That, however, didn't stop a seasoned English carpenter and clockmaker named John Harrison, who, after 30 freaking years of research, finally invented a reliable marine chronometer in 1735. Harrison was able to successfully test his marine chronometers over many different voyages, proving that his new clocks worked and were accurate. These low-friction, state-of-the-art clocks with special bearings and parts made of jewels would lose less than a second over a whole month. This was a technological revolution. Thanks to Harrison's chronometers, the British rapidly advanced their seafaring skills, leading to one of the largest empires in history, and unprecedented levels of oppression, theft, and cultural destruction. Oh, and remember that £20,000 reward? Funny story is, Harrison never got the full amount of this award. And in fact, no one did. The government kept coming up with excuses like, your machines just fluked it, and refused to pay him the prize, despite Harrison proving voyage after voyage that his clocks worked. Even when he produced 4 consecutively improved designs, the prize was nowhere to be seen. That said, Harrison did get a generous funding throughout the years that he worked on his chronometers, plus King George III helped mediate the partial awarding of money to Harrison, so by the end he did still get at least £23 from the government, which is not an unsubstantial amount of money. Technology improved more and more from there on, and clocks became smaller, cheaper, and more reliable, letting every ship carry chronometers to help figure out longitude and safely plot their journey. All thanks to accurate clocks, and the knowledge that knowing when you are helps you figure out where you are. Nowadays we have satellites and super accurate digital clocks and even GPS systems that let us accurately and immediately figure out what latitude and longitude we're in. This means we can navigate safer, make accurate maps, put down roads and railways to take us all over the world, and even do crazy things like drill 2 tunnels from either side of a giant mountain and meet right in the middle. Latitude and longitude let us plan better cities, let us communicate over oceans, help emergency response teams search for and rescue people in need, and overall, helps us better understand the pale blue dot that we all live on, through the advancement of geodesy. And to think that all of this comes from things like smart people such as Eratosthenes thinking about looking down wells on a summer day. Isn't science just wonderful? So, what did we learn today? We learned that coordinates are a useful way to know where you are in space, and to tell someone an exact location. We learned that the Earth is round, and mapping a grid to a sphere is tricky because of the curved surface. We learned that we can solve this with latitude and longitude, imaginary circles surrounding the Earth in even spaces, such that we have a coordinate system for the surface of the Earth. We learned what latitude and longitude are, how to interpret the numbers, and how they're useful, especially in navigation. We learned about the longitude problem, and how the knowledge of time lets you figure out distance, but how it was difficult to create a functional, accurate clock that worked on ships. Lastly, we learned how science and technology can make our lives so much easier, and even save people from death. Alright, for today's 2-Minute Explain, we've got a topic suggestion from Sigourney, asking us to talk about the astrolabe. We've mentioned all sorts of navigational technologies such as the sextant and marine chronometers, but the astrolabe certainly stands out as one of the most interesting historical navigational tools. The astrolabe is a beautiful, nifty circular device that looks like a giant clock. It is layers of intricately carved plates and moving parts that chart the entire sky, including sun positions, zodiac signs, and other major star positions at varying points of the year. It's essentially an armillary sphere, one of those old-school rotating spheres made up of rings and balls that depict all of the heavenly bodies moving around the sky, squished into a 2-dimensional shape. I'll post a picture of the astrolabe on the show notes, along with some maps and diagrams that really show you what latitude and longitude look like. In some ways, you could say that an astrolabe is the entirety of the visible universe zipped up in a device that fits in your hands. The astrolabe has many uses, kind of making it a medieval smartphone. But one of the key uses was to tell the time. To do this, you would first suspend the astrolabe on the chain, dangling it so that it would hang straight vertically. Then, you would take these 2 sights on one side of the astrolabe, and rotate the sights until the pinhole light shining through them matches up. This lets you figure out the angle of the sun's rays in relation to the horizon by looking at the line between the two sights. If you were to do this at solar noon, you'd actually be able to figure out your latitude. How handy! Telling the time with the astrolabe essentially takes this concept and flips it around. Because instead of calculating latitude, you take a plate of pre-recorded sunlight angles to figure out at what time would you expect to see a specific sunlight angle given that you know your latitude and what calendar day it is. So once you have the angle figured out, you would look at the opposite side of the astrolabe, where there would be a super intricate, elaborate edge plate marking all of the star positions, along with the zodiac signs marked along the edge of the circle. Remember back in episode 54 that the zodiac kind of acts like the numbers of a clock face, surrounding the Earth on this ecliptic plane, and how you can use this to map out where the sun is in relation to Earth by looking at what background zodiac sign the sun is crossing in front of? You remember all that, right? You've been paying attention? Well, using this knowledge, you can make a huge database or almanacs of sun position and angles, depending on where the sun is in the zodiac. The astrolabe contains all of this information in the form of etched curved lines. So for example, if you know that the sun is crossing Aquarius and it's been 14 days since this happened, you'd make a mark on the astrolabe saying Aquarius 14, that's the date today. This will take you to a curved line on the plate that essentially shows you the path that the sun takes in the sky on that given day. Using this curve, you can match the angle that you calculated to the time of day that you would expect the sun to be in that exact position. And huzzah! You figured out the time! Yes, it's a lot more complicated than raising your wristwatch or turning your phone on, but considering that people have been using astrolabes since about 900 AD, it's pretty dang impressive. The astrolabe can also be used to calculate your latitude, map stars to figure out what the night sky looked like on the day that you were born, to calculate the height of buildings using the sights in basic trigonometry, to surveying and architecture planning, and even siege warfare. It was particularly popular in the Muslim world where they were developed, but they had rapidly spread to Europe over the coming 400-500 years, where even Chaucer talks about the astrolabe. The astrolabe eventually became obsolete with better navigational technologies such as the sextant and accurate clocks. But it's still cool to think that people could figure out what time of day it is based on star charts and the angle of the sunlight and your relative latitude compared to the equator. Plus a lot of clever mathematics. And I, for one, appreciate that people value the knowledge of what time it is even 1,000 years ago. Well, that's it for today. Thank you for listening to Explain This. Hope you've learned something interesting and maybe even useful today. Now, I'm actually going to be away on a very long trip for the next 3 months, which means unfortunately there will be no podcast episodes for the month of May, June, and July. But I swear to you, I'm going to bring some good content back to you starting from the first Friday of August. So, hope you enjoy some backlog episodes in the meantime, and I will see you in August. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter.